Alright, welcome to Periodicity, which we are going to strive to cover all in one video, because periodicity, honestly, is just shockingly simple. What are we talking about? The periodic table. Do you remember the periodic table from back in middle school, elementary school maybe? They teach it pretty early nowadays. What is it? Well, it was a table, organization of elements made by our good old buddy Dmitry Mendeleev. You don't really need to know the story behind it. We organized the elements into a table, and it was useful. Why was it useful? Because we organized them in an order that reflected their properties, which is what we're discussing here, how the periodic table manages to reflect the properties of all the different elements in nice little groups. First off, we organize the periodic table by order of increasing atomic number. You go hydrogen with 1, helium with 2, lithium with 3, beryllium with 4, and go on and on and on and on and on. And kind of organize them where we got periods and groups. Periods are the sides, and as you go down a period, you add another energy level. You go from, if you remember back from our atomic structure video, the 1s orbital, now it's 2s. Period 3 is 3s. Period 4 is 4s. They're conveniently numbered like that. And then as you go across the groups, you add an electron. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. The transition metals are weird. Group 3 has 3 valence. 4 has 4 valence. Or 13, 3 valence. 14, 4 valence, as you would call it. And if you also remember from our atomic structure video, we can divide them into little blocks. You've got the alkaline and alkaline earths over here. First 2 groups are S block. All the transition metals are D block. The last few groups are P block, and the lanthanides and actinides are F block. And that just tells you the orbitals of which the valence electrons will be located in. Pretty simple. That's the basics of the periodic table. Now, there's one distinction we need to make. What is the difference between a metal and a non-metal? Well, if you look over here, well, it's called the transition metals, so it makes it kind of obvious. You look over here, you've got all the way over to sort of the middle of the P block there. You have your metals. And then, over there, those are non-metals. Now, what is the difference between a metal and non-metal? Well, you got to go into that, but metals, they have specific properties that are very different from non-metals. Metals tend to combine ionically, non-metals more like to do it covalently with each other. Metals tend to conduct electricity, and non-metals tend to not conduct electricity, and that sort of thing. And then you've got a sort of line of elements right along the border between the metals and the non-metals, which are called the metalloids. They do both. They like to be non-metals and metals. They're just kind of a combination of the two. And those are the key aspects of the periodic table right there. Now, periodic trends. Trends that we can discover along the periodic table. First off, physical properties of each individual element. To understand the physical properties, first we must understand effective nuclear charge, ENC. Now what is that? That is simply the charge or the attraction that's given by the atomic number between the protons at the center and the electrons that are floating around. So if you think of hydrogen, you've got a proton, you've got a single electron floating around, a certain degree of attraction that keeps that electron in its little orbital. And that's basically it. Now, the key thing about effective nuclear charge here is as you go down each period, you get a layer of shielding. Why? Because you went from 1s to 2s. Well, the 1s orbital still exists, right? And there's still 2 electrons in that 1s orbital, but now there's a 2s. So the outermost electron is shielded from our proton's love and attraction because they're electrons in the 1s orbital. And you know, electrons hate electrons. They want to get away from them as fast as possible. There's a certain degree of repulsion that electron will experience. So when you go from hydrogen to lithium, where now you have 2s, there's going to be a certain degree of more repulsion from the nucleus than in hydrogen. And that is reflected in our trend of atomic radius. Now, the idea of atomic radius is what's the radius of the atom going out to the furthermost electron. So it's not as simple as you might think, because as we saw in atomic structure, electrons occupy orbitals. So we don't know where the furthermost electron is. We just know where it could be. We have to figure out where it could be. So what we do is we take diatomic elements like hydrogen, we put them together, and we see how wide that is. And that must be right in the middle. That's where the dividing line is, and thus we have a radius. So what's the trend for atomic radius? Well, what ends up happening is as you head across, atomic radius actually gets smaller. Now why is this? Because as you head across each period, you add 1 electron, 1 proton. And the electrons, because there are more protons, get drawn in. drum it, drum it. However, as you go down a group, the atomic radius gets larger. Now, why is that? That's because now you have shielding. And so the shielding creates a degree of repulsion. So let's say you have hydrogen, you've got that one electron floating really close to the nucleus, right? And then you go to lithium and bam, now there are 2 electrons between that valence electron, and it's like, no, I hate electrons. And it goes out further. Bigger atomic radius. So as you go down a group, atomic radius gets bigger, and as you head across a period, it gets smaller. And that's the trend for atomic radius. Now, another thing we can discuss is ionic radius, which is the radius of ions. And what happens is when you have metals, they tend, when they form cations, they get smaller because they lost an electron. So the valence electron is no longer the outermost electron, it got thrown away, and now it's the innermost. And so what happens is it's pretty much the same. Positive ions, as I told you, are smaller than parent ions. Negative ions, like chlorine to chloride, well, they gain electrons, so they get bigger. They're larger than their parent atoms. Ionic radii will decrease from groups of 1 to 14 for the positive ion. So as you go across, the atomic radii gets smaller because, you added more protons, just like with atomic radii. And for the negative ions, they're going to decrease from 14 to 17 because you're adding more protons. Basically the same trend as before, just discussing in ions. Now, ionization energy. Ionization energy actually kind of has the almost exact opposite trend as atomic radius. As you go down, instead of getting bigger, ionization energy gets smaller. Why is that? Well, ionization energy is the energy that it takes to take that one valence electron away from the atom. That's the first ionization energy. And just like I discussed earlier, there's shielding. And that creates repulsion between the electrons and the electrons below it. So therefore, the effective nuclear charge is not quite as strong, and it's easier to pull that little electron away. And as you go across, it gets stronger because there's more protons, more attraction, and it's harder to pull away. And that's the general trend for ionization energy. Now, what about electron affinity? That's the energy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions. Now, it's kind of like the negative of first ionization energies. The group 17 elements, which is the halides, have incomplete outer energy levels and high effective nuclear charge. So they attract electrons the most because they really want to get those electrons to fill up to get their 8 noble gas stable arrangement. Group 1 metals have the lowest effective nuclear charge, and so they attract electrons the least. So electron affinities end up reaching a maximum for group 2 and group 5 elements. And so why is that? Well, because when you launch those electrons in to create the ions, the energy change is going to be greatest over in the negative because the most ions are created, so you get spikes there. Now, what about electronegativity? That's pretty simple. Halogens are the most electronegative because they have the most electron attractiveness, right? Electronegativity is the measure of the ability of its atoms to attract electrons in a covalent bond. So fluorine is going to be the most electronegative. Now, why not group 18? Because group 18 is the noble gases and they just don't react. And so group 18 is kind of like, for this trend, we cut it out of the table because noble gases don't react. But then generally, electronegativity increases across and it also increases up. And that's the trend for electronegativity. So now you can kind of see a clear connection here. Metals end up having lower ionization energies and electronegativities than nonmetals. Metals, it's easier to take their electrons away, and they don't really want them back. Nonmetals, they really don't want you to take their electrons, and they want some of yours. They're like burglars. But that's the basic distinction. That's the basic chemical, physical distinction between nonmetals and metals. Now, let's discuss melting points. Melting points are a bit more complex than all the other trends because they kind of spike in the middle of the periodic table. And that's because the elements that have metallic structures and they bond metallically. We'll talk more about this in our our bonding chapter, but what happens when metals bond is that they release their electrons and they create this kind of sea of floating electrons that really makes them come together. So right in the middle of the transition metals, it's where it's hardest to melt things. Out by the alkali metals, out by the halogens where they bond covalently, not so much. They melt easier because they don't bond together metallically as much. Because, you have more electrons than the transition metals. Over here with sodium, you got like one valence electron. That electron C is going to be pretty small. But over here with iron, where it's got 26 freaking electrons, it's all this giant sea of electrons, and they're all being attracted together. Now, finish the physical, onto the chemical. Chemical properties pretty simple. Group 18, noble gases, they don't react. That's really it. They've got their wonderful octet of 8 electrons. Helium has 2, but helium only needs 2, and so they don't react at all. That's it. Group 1, alkali metals, they like to react a lot. Why? Because they only have 1 valence electron. They want to get rid of that, so the shell below it, which already has 8, is now their valence electrons, which is the stablest. So what will they do? They will react with anything and everything. They like especially to react with water. And it gets more explosive and more reactive as you go down the period. If you put a piece of lithium inside water, it'll just kind of float around and slowly dissolve. Sodium will catch fire. Potassium will explode. Keep going, the explosions get more crazy. If you dumped a block of cesium into a river, it would cause an explosion so spectacular that you might get some acid in your eyes. So don't do it. And that's basically that. Group 17, the halogens, also very reactive. They have 7 valence electrons. They want 1 more, super electronegative. They want to steal your electrons. So fluorine is going to be the most reactive. And as you go down, they get slightly less reactive. So what they're going to react with, well, wait, the halogens really want an electron, and the alkalis really want to get rid of 1 electron. So they often react to form ionic halides, like table salt. Sodium and chloride combine to form sodium chloride, or table salt. And that's the basic reaction between those. And because fluorine ends up being more reactive than all the ones below it, you can do displacement reactions with halides, where you'll chuck together some sodium fluoride and some aqueous sodium bromide and, well, let's say aqueous silver bromide, and what you're going to get is silver fluoride and some aqueous bromide and sodium floating around, because the fluorine, being more reactive, just stole bromide's date and took his partner. And that's displacement reactions that you perform with the halides. Finally, we are going to discuss the period 3 oxides, because they help to explain a basic trends that you see in all the other periods. So let's talk about period 3. What is period 3? It's sodium, magnesium, aluminum, because it doesn't have any transition metals, silicon, phosphorus, sulfur, and chlorine. And I mean, I guess you can include neon if you want. Argon. You can include argon, but it's a noble gas. We don't really care about it. So let's talk about that. They each form in different ways. For example, when you have sodium and magnesium and aluminum, when they bond, they're going to form ionic superstructures. They're going to form the ionic crystal lattice. However, when you have silicon is going to form the covalent superstructure, which is slightly different. We'll discuss it in our bonding chapter. And then phosphorus, sulfur, and chlorine are all going to form various covalent structures. Phosphorus has got 5 phosphoruses that bond together. Sulfur's got, I think, like 3 sulfurs that bond, I believe. And chlorine's diatomic. And so those are different ways of bonding that end up creating a few different properties among them. For example, the ionic superstructures are very good electrical conductors. The covalent superstructure, not so much. And all the regular covalent ions, well, they're not. Now, why is this? Well, ionic superstructures have ions all connected, rubbing up against each other. Same thing with covalent superstructures, though not quite as much. But covalent structures, the electrons are trapped in their covalent bonds. You've got 2 chlorines floating around, 2 chlorines floating around. They don't want to trade electrons, so no electrical conductivity. So, then, you can talk about the oxides. Acid-base character of the period 3 oxides. Well, what's going to happen? Don't have to explain why, you just have to know it. When you go from sodium to magnesium, sodium, magnesium, basic. Aluminum, amphoteric. Silicon to chlorine, acidic. That's what happens when they form oxides. They just happen, the nonmetals become acidic, metals become basic. That guy sitting in the middle, aluminum, ends up being amphoteric. So sodium oxide and magnesium oxide will dissolve in water to form alkaline solutions, owing to the presence of the hydroxide ions that form, because sodium is going to end up bonding with sodium hydroxide, with the hydroxide, and while the other ones are going to bond with hydronium ions instead. And that's the basic idea. Aluminum is amphoteric because it could bond with hydroxide or hydrogen. It doesn't really care. And that's it. That's periodicity, folks. Join us next time to discuss bonding, chemical bonding, and structures.